Hi everyone. Today I'm going to discuss about our paper on accurate detection of wake word start and end using a CNN. My name is Christin. I'm an applied scientist with Amazon Alexa Speech. And these are my co-authors. Let me start with the motivation. What is a wake word? So wake word is described as a keyword that is used to wake up a voice assistant enabled device like an Amazon Echo, a Google Home, etc. So here I have like a hypothetical audio stream telling like Alexa, how are you? So the problem here which we are trying to solve is accurate detection of the wake word start and end. That is like the start of Alexa and end of Alexa together with the wake word detection. So let me start with the summary. So this project entirely focuses on small footprint embedded devices that require keyword spotter, and this model should be small in size with a minimal latency for enabling voice assistance. This model is required to detect wake word together with accurate estimation of the wake word start and end. This will ensure that we send the right audio to the cloud and also help to ensure user privacy. In this paper, we propose new methods for detecting the endpoints of the wake word using a single stage word level CNN network. The two new methods we propose give superior accuracy for wake word endpoint detection when compared with a simple method using a constant offset, and also it's on par with conventional acoustic model plus HMM forced alignment method, while our new method being much simpler to train and it can well work on resource constrained devices. So this is the outline of the presentation. So first we'll discuss about related works. So always I wish to start the related works with the conventional wake word detection methods that uses a two-stage model architecture. First being a neural network, which acts as an acoustic model, and the second being an HMM, which detects which orders the outputs of this DNN in a way that it represents a word, or it can be like a sentence as well. So, and also coming to the recent works, like a lot of works investigated into single stage architectures of DNNs, CNNs, and even RNNs. So here we are focusing mostly on CNNs because our method works. It's based on a CNN. But the problem with the single stage architectures are it doesn't give accurate wake word endpoints. It just detects like whether the wake word is present or not and give like an approximate presence of the wake word, like where in the stream is, but it's not accurate. Just to also give you an idea how like a two-stage architecture worked. So it has like posteriors produced by an acoustic model DNN. It'll be like a set of synons, and an HMM is tuned to force align the sequence of synons and to see whether a wake word or a keyword is present or not. And the important thing here is based on the first and the last synon of a keyword or a wake word, we can know exactly where the keyword endpoint. Now let us go in explaining what a word level keyword spotting is. As the name suggests, this is a neural network which takes in like the entire context of a keyword or a wake word. So the input can range up to a second depending on the wake word length. So during the training time, the wake word is consistently aligned in the long input window, such as center. As explained, the model learns the probability of the presence of the wake word. So, and below is the architecture which we use in this study or in this project. And this is the wake word detector which we use. And to this wake word detector, we are adding the capability of the start and end point detection of the wake word. So currently this detector only detects wake word. It doesn't like predicts the endpoints of the wake word. As you can now, let us explain the new methods, the proposed methods. for endpoints detection in the previously described word level architecture. The first method, it's called the start and regression method. So here it's a simple idea here. So what we do here is we train a new network with the intermediate output of the existing architecture or the word level CNN, and we train this new network to detect the offsets of the Wacode endpoints in the input window. So this is done to ensure that we don't degrade the Wacode detection performance of the original network. So as you see here, this is the original network, and it's frozen. So we don't train it in a multitask manner. So we freeze the first Wacode detector network, and we train the other network as a branching network using the intermediate output from this network. And we chose like which layer to branch based on like controlled experiments to see which output gives the most accurate endpoints. And the second network is a very minimal network. It has just like a convolution layer followed by a fully connected layer with two outputs. Now coming to the second proposed method, it's called multi-aligned Wacode model. As the name suggests here, this has aligned outputs. So let me explain you what is an aligned output. So here we use the same network here. So we have the same word level CNN. We add two more outputs to the network, and it's called like start output and the end output together with the Wacode output. And let us see what are those new outputs. So whenever each of these output happens, we can detect start, end, or the center of the Wacode. So during the inference time, what happens here is, so if you see here, whenever the pause center align output happens, we know that like the start of the Wacode is in the center of the input window. So we can just subtract that specific offset, that is like half of the input window size, to get the start of the Wacode. And similarly for end aligned, whenever that a posterior spike happens for that output, we will see that like end has happened. So it's a pretty cool way to see like detect the start and end of the Wacode. And one more thing which I want to explain here is like the reasoning behind the peculiar start output, like aligning it to the center of the input window, like aligning the start rather than placing the start to the start of the input window. The reason being latency, because for such an alignment to happen, we have to wait after the center alignment for the start alignment to happen. So we figured out that like placing the half Wacode, like half or towards the center, it will save the latency. So we have like a low latency start detector. And coming to the experiments and results now. So we evaluated the endpoints generated by both of these methods with the 33K streams, annotated, held out streams. And so for the ground truth of this 33K streams was not like human annotated. It was like it was annotated using like a two-stage AM plus HMM keyword spotter. The reason being the human annotation was laborious, so we didn't have like a mechanism to label it. But the main agenda of this entire project was like to have a method which is on par with the AM and HMM KWS method. So we used that as our pseudo ground truth. Additionally, we also have a smaller data set that is human annotated, but it was only annotated for start. There is no endpoint annotated, but yeah, it has it will give us some idea like where the start was detected by these models. And also the thing is that it was in 5 different noise conditions as being seen here. And this is the simplest method which you can have in a word level model. So I chose this as like a comparison in the tables for the 33K streams, the larger data set, just to give an idea like how far we have improved from like a constant offset endpointing. Something like when the detection happens, we subtract a constant offset, which can be like a median or mean wake word length, and how far we have improved from this one. So let us see the results. So if you see here, the results are in multiple rows here. So this is the constant offset method, which I explained just before the slide. And we can see the standard error for start, standard error for end. And this is for all streams. And we have a separated analysis for long wake codes that is like more than 800 millisecond in length. And also there is a column for wake code detection accuracy, just to see like where these new models are with wake code detection, whether it degraded or if it improved. Yeah, so those are the things addressed here. And based on the results, we see that the new methods make a significant improvement for the wake code start and wake code end. When compared with the constant offset method, we see like it's well under like 20 millisecond for start and under 50 millisecond for end. And to compare the regression with the align model, the two methods which we proposed, the align method slightly edge over the regression method for end, because we see, especially for longer wake codes, we see that the regression method is not that great. Like it's in this order, like 73 millisecond, but the align method is still doing a good job in detecting end. And also the important thing here is the wake code detection accuracy remains constant as for all these methods, except in one case where the regression method was trained in a multitasking manner. Like the main detector, the wake code detector network was not like frozen. It was like trained in a multitask manner, and so that showed some degradation. So that's the entire reason why we trained the regression method by freezing the main wake code network. So now let us go into the second data set, analysis on second data set, which is human annotated, only on start points. And we see actually the baseline model here is a two-stage architecture, AM and HMM, which is a gold standard for endpoints. So we see here the start point detected by the AM and HMM is same as exactly the one detected by our new methods, which is good actually. So that was our goal of this entire project. So we were able to get an on-par performance with the two-stage gold standard architecture. And also one more entry is for a second human annotator. So that shows like the variation in like annotating the start and end of a wake word. Even a human annotator can make a mistake of around 30 milliseconds. So our models are pretty getting closer to that, the human error, but they are still not there, but it's a good data point to show here. Now, coming to the future work. So the future work, one thing can be done here is use the post sender output, because it's a low latency detection of wake word. It can be used in a cascade architecture setting where there is a first stage model which needs like a low latency wake word detection. It needs to be very permissive. It should be good with recall. So that's a good output in that case, and also in a VAD settings, voice activity detection. And the other experiment which is currently in progress is like combining all the outputs, like the start output, the end output, and the wake code output of the multi-aligned approach, to use it together for wake code detection. So currently we explored it using OLIF for start and end detection, and we use the wake code output for wake code detection. So the new work which we are doing is like trying to combine all of them to improve the wake code detection. Just to like give an idea of what we discussed so far and give you a conclusion, we proposed two new methods for wake code endpoints detection for a word level keyword spotter, namely the start and regression model and multi-align modeling method. So we found that we made like a standard error under 20 milliseconds when compared with the gold standard AM plus HMM. And this is a pseudo label data by that model. And also the endpoint detection was within 50 milliseconds. And the interesting thing here is when we compared with the human annotated data, we saw that like it's on par with the gold standard two-stage model. So that is a summary of this work and the improvements which we made. So thank you all again, like for listening to this presentation. I know it's like a hard time asking any questions, but I appreciate if you can like send me an email if you have any questions. Feel free to send me, and I would love to like reply with any queries on this presentation. Thank you again so much for attending this presentation.